Hey guys, this is Professor Janacek. Today I want to talk about absolute convergence. To check if a series is absolutely convergent, what we'll do is we'll take a look at the absolute value of the terms in the series. If the series of absolute values converge, then our original series we say is absolutely convergent, or it converges absolutely. Now, if the series converges absolutely, then we also know that the series converges. That's kind of obvious. However, if the series converges but it does not converge absolutely, then we say that it converges conditionally or is conditionally convergent. Let's take a look at some examples. Suppose we have the sum, as k goes from 1 to infinity, of -1 to the k plus 1 over the square root of k cubed. All right, well, I do recognize this as an alternating series, but we can check absolute convergence on this. So let's consider the series where we take the absolute value of the terms. Well, in this case, that numerator, since it's alternating between +1 and -1, when I take the absolute value of that, absolute value of 1, absolute value of -1, they both end up being positive. So it turns out I can drop off the absolute values in the numerator and I just get a 1. In the denominator, it's not quite as easy to see, but I notice that my k's go from 1 to infinity. Those are only positive values. The absolute value of a positive value is still positive. So in the denominator also, I can simply remove those absolute values and it still remains the same. Let me go ahead and rewrite this just so we can work with it a little easier. In the denominator, the square root of k cubed is the same thing as k to the 3/2 power. And I recognize that 1 over k raised to a power looks like something familiar. Turns out that this converges by the p-series test. With the p-value of 3/2, which of course is greater than 1. So, what we've decided is that the series of absolute values converge. Well, if the series of absolute values converge, then my original series over here, we say, converges absolutely. Let's take a look at the series where k goes from 1 to infinity of the sine of k over k cubed. To determine absolute convergence, I want to consider the series where we take the absolute value of those terms. All right, well, let's see, can we simplify this a little bit? Well, turns out in the denominator, that's an easy one to see, my k values go from 1 to infinity. All positive values, taking the absolute value of a positive value, also positive value. So in the denominator, I can get rid of those absolute values. However, in the numerator, sine of k, well, depending on what k is, it could be a positive value, it could be a negative value. So we can't really get rid of the absolute values there in the numerator. So now what to do with this series? Well, by the direct comparison test, since our a sub k's are the absolute value of sine of k over k cubed, we need to come up with some b sub k's that we can work with. Let's try 1 over k cubed. I notice that sine of k is bounded above by 1, which means that my a sub k's are less than or equal, or actually just less than my b sub k's. That's the first part of the direct comparison test. The second part is now to look at the limit, to look at the series of just b sub k's. Well, that is the sum as k goes from 1 to infinity of 1 over k cubed. And this one I see converges. Again by the p-series test. With our p-value equal to 3, which again is greater than 1. So, what have we found? The b sub k's converge, that's the first thing, and the a sub k's are less than the b sub k's. Remember what that looks like. The a sub k's are smaller, the b sub k's converge, so remember the a sub k's cannot go crazy under there, they have to also converge. So that means my a sub k's converge. Remember my a sub k's originally came from the absolute value. So we know that the series of absolute values converge, which means my original series, the one I started with back there, we can say converges absolutely. And there we go. Enjoy!